V2 using nodal analysis technique. Now, before I even go through the steps of how to solve the circuit, we wanted to introduce few definitions. So before we do the nodal voltages, we need to look at the circuit and we need to recognize the different nodes that we have. And I'm going to start with the reference node. Now keep in mind that the node is a point at which two or more elements or branches are connected, and you always consider the short circuit to be the same node. So for example, if you look into this bottom part is one single node, and we're gonna call it the reference node. So over here, this is the reference node, and the reference node basically means that the voltage at any other node gonna be measured in reference to this node. So this node physically, in most cases, is connected to ground. So this symbol here means that it's connected to ground. That means it reads 0 volts in reference to any other node. Now this is one single node as shown here, because this branch, which is the current source, this branch, which is a resistor, this branch, which is another current source, and this branch, which is a voltage source, are connected at the same node. Now keep in mind that all those short circuits are the same node. So all those short circuits are considered to be the same node because there is no branches or elements connected between them. So this is the first node that we have in the circuit. Then we're gonna look at this node. This is another node. A node is defined as two or more elements are connected at that point. So at this point we have this element and this element are connected, so this is a node. And now we're gonna define the nodal voltage. So the nodal voltage is basically the voltage from this node to the reference node. So the polarity of the voltage gonna be like that. It's the plus polarity at the node and the minus polarity gonna be at the reference node. So clearly that the nodal voltage, which is the voltage at this point in this particular node, is the same as the 10 volts, because the 10 volts voltage source basically states that it is the voltage from the reference node to this node. So the voltage going to be basically 10 volts. Now keep in mind that you're going to be consistent with the polarities here. So if we reverse the polarities, if we make this voltage source, for example, to have the plus polarity at the bottom, then the voltage at this node going to be negative 10 volts, because the voltage from this node to ground then going to be minus the voltage from the plus to the minus. In any case, we have consistent polarities here, so the plus polarity on the top is the same as the plus polarity on the top of the voltage source. Then the nodal voltage going to be 10 volts. So then we have another node which is at this point. So this point where we have three elements are connected at this point. So the voltage at this node is not clear because we don't have a voltage source connected from this node to ground. Then we don't know what the voltage is. We need to solve for it, and we can do that using the nodal analysis techniques. Also, the voltage at this node going to be from this node to ground, like we stated. So the voltage from this node to ground is the nodal voltage, and we're gonna give it a name V1. We give it a name V1 because we don't know what that voltage is, so it is unknown nodal voltage. Also, we have another node over here. So this node is basically where we have the three branches are connected, this resistor, and this current source. Now keep in mind that this short circuit is the same node, right? So the short circuit is the same node. So this is the second node, we call it V2. And the nodal voltage at this node is basically the voltage from this node to ground, right? So from this node to ground is the nodal voltage. And clearly that this nodal voltage is unknown because we don't have a voltage source connected from this nodal voltage to ground. So if you look into the circuit, basically you're going to say that we have two unknown nodal voltages, and we need to solve for those nodal voltages. Before we even apply the nodal techniques, we need to stress a couple of things, and we need to look at how we can evaluate the voltage across a resistor, for example, like the voltage across this resistor, for example, R2. So we're going to define Vx to be the voltage from the left to the right of the R2. So here we say that Vx is going to be the voltage from the left to the right of R2, and we're going to solve for this voltage in terms of the nodal voltages by applying KVL. So I know that the voltage here is going to be the nodal voltage V1, because the voltage from the bottom to the top is V1, and the voltage here also from the bottom to the top is going to be V2. Now we're going to apply KVL here. So let's see what happens when we apply KVL. My convention is to go clockwise. If I enter the negative polarity, going to be minus. If I enter the positive polarity, going to be a plus. Then by KVL, I'm going to have minus V1, that's the nodal voltage V1, plus Vx plus V2 equals 0. This here is a single loop. So that's what we have, minus V1 plus Vx plus V2 equals 0. So if I'm going to solve for Vx, basically I'm going to take V1 to the other side and V2 to the other side. So the negative V1 is going to be positive V1, and the positive V2 is going to be negative V1. So Vx will equal to V1 minus V2. Now we're going to take this over here and see how we're going to define Vx without using KVL. It's basically a shortcut. So if we say that we wanted to solve for Vx, where Vx going to be the voltage from the left to the right, then Vx going to be V1 minus V2. The voltage on the left minus the voltage on the right. You look at the polarity side, you say that the voltage at this node, which is V1, minus the voltage at the other node, which is V2. So Vx going to be V1 minus V2. So basically we can use this equation right away, right, without using KVL. Now if we define Ix, where Ix will be the current enters the resistor from the left. So the current enters R2 from the left. Well, we know that Ix relates to Vx because this is Ohm's law, right? The current will basically be the voltage across the resistor over the resistance itself. So what's Ix will equal to by Ohm's law? By Ohm's law, it's going to be the voltage across the resistor, which is Vx, over the resistance. So Ix will equal to Vx over R2. But we already know that Vx is nothing but the voltage on the left minus the voltage on the right, so it's going to be V1 minus V2. So we can state that Ix will equal to the voltage at the side where the current enters the resistor, that's going to be V1, minus the voltage at the side where the current leaves the resistor, that's V2. So it's going to be V1 minus V2, that's the voltage across it, over the resistance itself. So we can say that Ix will equal to V1 minus V2 over R2. So we don't need to basically go over current will equal to Vx over R. Basically we're going to say that the current will equal to V1 minus V2 over R. Right? For the same resistor, I'm going to flip the polarities. I'm going to call Vy to be the voltage from the right to the left. By the same analogy, you're going to say that Vy going to be V2 minus V1, the voltage where the plus polarity is. So that's the nodal voltage V2 minus the nodal voltage where the negative polarity is, that's going to be V1. So we can say that Vy will equal to V2 minus V1. And we don't have to use the KVL equation because we already know that by KVL it's going to be the voltage where the plus polarity is minus the voltage where the negative polarity is. We don't have to write the KVL equation because we know that this Vy going to be the nodal voltage where the plus polarity is, that's V2, minus the voltage where the negative polarity is, which is V1. So it's going to be basically be V2 minus V1. That's what we have here. Vy will equal to V2 minus V1. Also, if we decided to say that find the current enters the resistor from the right, so this current basically right away going to be V2 minus V1, that's the voltage across the resistor, over the resistance itself. So that's what we have, the current going to be V2 minus V1 over R2. So in summary, the current going to the right, going to be the voltage on the right, that's V1 minus V2 over the resistance. Or if I say that give me the current that's going to the left, it's going to be V2 minus V1 over the resistance, right? Clearly that those two currents going to have the same magnitude but opposite signs, right? So those are some of the basic things that we wanted to know before we use the nodal analysis technique. So now let's start doing the nodal analysis technique, and let's see how we are going to solve for the nodal voltages V1 and V2. Now the basic idea is basically to apply KCL at every unknown node in the circuit. So this circuit, we have two unknown nodal voltages, V1 and V2. Those are the only voltages we don't know. I know the voltage here to be 10 volts, and the voltage here is 0 volts. I don't know what's V1, I don't know what's V2. So we're gonna apply KCL at node V1, we're gonna apply KCL at node V2. We will end up with two equations, two unknowns. We call them system of equations. And then from there, we will be able to solve for V1 and V2. So we're gonna start by applying KCL at V1. So I'm gonna come to V1 here, and we're gonna apply KCL. Now the way I apply KCL at V1 is to sum all the currents leaving the node. So my convention is sum all the currents leaving the node equals 0. So if all the currents will leave this node, the sum of all the currents leaving the node will equal 0. So this is my convention. So the way I'm gonna do it is I'm gonna start with the current leaving this resistor, which is the 10 ohm resistor. Now this current going to be the voltage at this side, which is V1, minus the voltage at this side, which is 10, over the resistance, which is 10 ohms. So when we apply KCL, we're going to say that it will be V1 minus 10 over 10 volts. Now I'm going to add the current leaving this branch. Now the current leaving this branch is the same as the current source. So the current source here is basically how much current leaves this branch. So the current will leave this branch going to be basically 0.21 amps. Because it is leaving, I'm gonna add 0.12 amps. Finally, the last current will leave this node gonna be the current leaving this resistor. So the current leaving this resistor will basically say that the polarity gonna be higher at V1. So the voltage across this resistor by Ohm's law gonna be V1 minus V2. If we divide by the resistor, gonna give us that current. So this current gonna equal to V1 minus V2 over that resistor. So I'm gonna come to the equation. I'm gonna say that V1 minus V2 over 12 ohms, and this will equal to 0. So here we have this first equation, but this equation is not well organized. So we need to organize this equation so that we need to express it as a system of equation in terms of V1 and V2. So the way we're gonna do that is we're gonna group the V1 terms together. So I have two terms for V1. I have this term and this term, and then I'm gonna group the V2 terms together, which is this term here, and then I'm gonna take the other values to the other side of the equation. So I'm gonna start with the V1. So I have those two terms for V1. I have V1 over 10 plus V1 over 12. So I can state that it's gonna be V1 times 1 over 10, that's for the first element, plus 1 over 12. Now, I don't recommend the students to use common denominators. I recommend students to enter the values like that. So I would recommend you to enter the values like that for the V1 terms. Now I'm going to enter the values for the V2 terms, and the V2 terms basically going to be negative 1 over 12. So I'm going to say minus V2 of 1 over 12. And then I'm going to take the other two terms to the other side of the equation. So I have two terms, this term and this term, I will take them to the other side of the equation. So I will say that this will equal to the negative 10 over 10 becomes positive 10 over 10, and the positive 0.21 gonna be negative 0.21. So this is the way the equation will look like. Still, it doesn't look nice, but we can evaluate this value here using the calculator, this value using the calculator, and this value using the calculator. So we can simplify the equation and it can look in this form. Now we have 0.18333 times V1 minus 0.08333 times V2 will equal to 0.79. So this is the first equation that we obtained from summing the currents at node V1. So clearly from this equation we have two unknowns and one equation, so we can't solve for V1 and V2 yet, right? So now we're gonna use KCL at the second node. So at the second node we're gonna use KCL. We're gonna come to V2, we're gonna apply KCL at this node, basically apply KCL at node V2, right? So that's what we have here. So we're gonna sum the currents leaving the 12 ohm resistor. Again, my convention is to sum the currents leaving this node. So the current leaves this node going to be V2 minus V1. That's the voltage across the resistor over the 12 ohm. So I can state that to be V2 minus V1 over 12. That's basically the current leaving this resistor, plus the current leaves this resistor over here, and the current leaves this resistor is going to be basically be the voltage on the top, which is V2 minus 0 over the resistance, or simply is going to be plus V2 over 13, right? So V2 minus 0 is basically V2. That's the voltage across this resistor. Divide by the resistance, which is 13. That would give me the current through the 13 ohm resistor. Plus the current leaving this branch. So the current leaving this branch going to be negative or minus the current going into the node, right? Because we know that the current leaving this branch is the same as the current source in magnitude, but an opposite sign. So we're gonna say that the current leaves this branch going to be negative, this current. So that's basically gonna be minus 0.53, and this will equal to 0. So this is basically the sum of the currents at node V2. Now we're gonna organize the terms. So I have only one term for the V1. So I'm gonna say that V1 times negative 1 over 12. And then we're gonna add the V2 terms. We're gonna have plus 1 over 12 plus 1 over 13. And I'm gonna take the last element to the other side of the equation. So this is going to be equal to 0.53. And when we clean this equation, what we're going to have is negative 0.08333 times V1 minus 0.160256 V2 will equal to 0.53. This is the second equation of the second node. So now we have two equations to unknowns. Now there is different techniques to solve for V1 and V2 when you have system of equations, two equations to unknowns. One of them will be back substitution. The other one will be the Cramer's rule, and the fourth one will be the matrix form. I like to use the matrix form because most modern calculators will do that. If you have a calculator that will solve a system of equations, then go ahead and use it. Other than that, you're going to use either back substitution or Cramer's rule. Either way will work. So I used here the system of equations. So I'm going to enter the equations into a matrix form. So basically I will have 2 by 2 matrix where I'm going to enter the coefficients of those matrix, right? So the first equation here going to have, this is the first coefficient of V1, this is the second coefficient of V2, this is the first coefficient of V1 in the second equation, this is the second coefficient for V2 for the second equation. So those coefficients are multiplied by the vector V1 and V2. Now you need to make sure that the order of the equations is correct, right? So make sure that you are a little bit articulate and organized when you set the equations. So you always set V1 and then V2, and here you're going to set, or you're going to write down V1 and then V2, so that when you transform this equation to the matrix will be straightforward. This will equal to basically the other side of the equation, which is the 0.79 and the 0.53. So you converted those two equations into a matrix form, and now solving for V1 and V2 is very easy. V1 and V2 going to be the inverse of this matrix multiplied by this vector. Right? Most modern calculators will do matrix equations, will solve two equations, two unknowns using matrices. Now when you calculate this matrix, the inverse of this matrix, what you're going to have is V1 going to equal to 7.611 volts, and V2 will equal to 7.265 volts. So we were able to solve for V1 and V2. Now, what's important is once you solve for V1 and V2, and you already know the voltage here is 10 volts, you can solve for any current and any voltage in the circuit. So for example, if you want to solve the current going this way, from the left to the right through R1, is going to be 10 minus V1, which we already know, divided by the resistor. If you want to solve for the voltage across this resistor, it's going to be 10 minus V1. If you want to solve for the voltage across this current source, it's going to be V1. And the current through it is already known. If you want to solve for the voltage across this resistor, it's going to be V1 minus V2, which you already know the values for. If you want to solve for the current, you're going to say that V1 minus V2, which you already know the values for, divide by the resistor. So you solve for the voltage and the current through here. The same story here. You know that the voltage across this resistor is going to be V2. So is the voltage across this current source going to be V2. And then the current through this resistor going to be V2 over R3. So once you solved for the nodal voltages, you can solve for any current or any voltage in the circuit. And that is very powerful technique. That is why we call nodal analysis is a universal technique. That means it will solve for any circuit problem. So any circuit problem that you have, you can always